Converting polar equations into rectangular equations. There are a couple of things we need to remember from college algebra and from converting polar coordinates into rectangular coordinates that were discussed earlier in this unit. First, we need to recall that the equation x minus h squared plus y minus k squared is equal to r squared is that of a circle with the center at the point h comma k and with a radius of r. Second, recall that we need to use x is equal to r cosine theta and y is equal to r sine theta to convert polar coordinates into rectangular coordinates. We also used x squared plus y squared is equal to r squared and tangent theta is equal to y over x when converting from rectangular coordinates to polar coordinates. Our job today will be to convert polar equations into rectangular equations and vice versa. This is a polar equation that can be entered into our graphing calculator and see what the graph looks like. We can also convert this equation into a rectangular equation. Let's first start by squaring both sides of our equation so that we get r squared is equal to 9. From right triangle trig, the Pythagorean theorem, and from converting coordinates, we know that x squared plus y squared is equal to r squared. So our equation now becomes this. This equation looks like the equation of a circle where the center of the circle is at the origin and the radius of the circle is 3. Therefore, we can conclude that r is equal to 3 is a circle with a radius of 3 whose center is at the pole. And we can see this on the graphing calculator when we graph r is equal to 3 in polar mode. This makes sense because if we were to graph points of r is equal to 3, we will find the points will be in the form of 3 comma theta. That means for at any angle theta, we can connect all these polar points that are in the form of 3 comma theta, and we see that these points plot a circle on the polar graph. Let's try another example. Unlike the example before, we cannot put this equation into our graphing calculator, so we must rely on the rectangular equation to determine its graph. From our bank of relationships we know that tan theta is equal to y over x. So let's take the tangent of both sides to get tan theta is equal to tan 5 pi over 6. From our unit circle, this now becomes tan theta is equal to negative square root of 3 over 3. Remember that tan theta is y over x, so changing that we get y over x is equal to the negative square root of 3 over 3. Now we have an equation with x's and y's only, so we have a rectangular equation. Solving for y, we have y is equal to negative square root of 3 over 3 times x. This is in the form of y is equal to mx, where m is the slope of a line. So theta of 5 pi over 6 is in line with the slope of negative square root of 3 over 3 going through the origin. This makes sense because if we were to graph points of theta is equal to 5 pi over 6, we will find the points will be in the form of r comma 5 pi over 6, regardless of the r value. If we connect all the polar points that are in the form of r comma 5 pi over 6, we see that these points plot a line going through the pole or the origin of the polar graph. Don't forget that r can be negative, so we can get a line crossing the entire graph. Now let's try some more complex looking examples. Example number 2. In this equation we have r, so we need to multiply both sides by r to get r squared is equal to 6r cosine theta. The good news here is that we can convert r squared and we can convert r cosine theta. So we get x squared plus y squared is equal to 6x. Now we have an equation with x's and y's, so we make it look like something we can recognize. In fact, let's write the equation and notice the space that I left after the 6x. I did this so that we can complete the square for the x's. This should remind you of the review where we completed the square for y is equal to x squared plus minus 6x. So we need to add 9 to both sides of our equation. Let's factor the perfect square trinomial into x minus 3 squared plus y squared is equal to 9. This equation should resemble the equation of a circle with the center at 3, 0 and the radius of 3. So r is equal to 6 cosine theta is the equation of a circle of x minus 3 squared plus y squared is equal to 9. Now try example number 2, part B, where r is equal to sine theta on your own. You may want to pause this video to try this problem on your own. This problem is very similar to that in part A. The video will continue without audio so that you can see what you need to do to convert this polar equation into a rectangular equation. Now let's try a different looking type of polar equation. Example number 3. Recall that the reciprocal trig properties, in particular the secant theta, is equal to 1 over cosine theta. In our equation will now become r times 1 over cosine theta is equal to 4. Remember, when multiplying with fractions, top times top and bottom times bottom, and we get r over cosine theta is equal to 4. To get rid of fractions, multiply both sides of the equation by cosine theta to get r is equal to r cosine theta. This should remind you of the example for number 2a. Multiply both sides of our polar equation by r to get r squared is equal to 4r cosine theta. Now we can convert this from polar to rectangular using x squared plus y squared is equal to 4x. And this sends us back to completing the square in order to complete the conversion from a polar equation to a rectangular equation. Now try example number 3b on your own. You may want to pause this video to try this problem on your own. This problem is very similar to that in part A. The video will continue without audio so that you can see what you need to do to convert this polar equation into a rectangular equation. Now let's combine what we know for example number 4. First, let's multiply both sides by r so that we get r squared is equal to 6r cosine theta plus 8r sine theta. So we're going to convert what we know. So x squared plus y squared is equal to 6x plus 8y. Now we have it in rectangular, we make it look like a circle equation by completing the square. So reorganizing, we have x squared minus 6x plus y squared minus 8y is equal to 0. Notice the spaces that are left after the 6x and the 8y. In particular, we add both 9 and 16 to both sides so that we can regroup our equation and factor so that we have x minus 3 squared plus y minus 4 squared is equal to 25. So we can now see that this is a circle with the center at 3, 4 and a radius of 5. So far, we have been converting polar equations and finding them to be equations of circles. Now let's create a polar equation for a given circle. Let's create the polar equation of a circle with a center of -2, 1. Let's begin by putting our information into a rectangular equation of x plus 2 squared plus y minus 1 squared is equal to 0. We set it equal to 0 since the radius was not given. In fact, a circle with a radius of 0 is just a point, so we only have a point. Now let's get rid of parentheses by doing FOIL, and we get the following: x squared plus 4x plus 4 plus y squared minus 2y plus 1 is equal to 0. Rearranging and adding like terms, our equation becomes x squared plus y squared plus 4x minus 2y plus 5 is equal to 0. Equations written in this form are said to be written in general form, and we will be discussing general form of conic sections later in this semester. For our purposes, we are going to ignore the plus 5 and change our equation to x squared plus y squared plus 4x minus 2y is equal to 0. Using our conversion relations, x squared plus y squared is equal to r squared, 4x is 4r cosine theta, and negative 2y becomes negative 2r sine theta. So we're going to get the equation r squared plus 4r cosine theta minus 2r sine theta is equal to 0. Let's rearrange the equation so we have r squared is equal to a positive 2r sine theta minus 4r cosine theta. Remember, we're solving for r, so I'm going to divide both sides by r, and I get r is equal to 2 sine theta minus 4 cosine theta. This is our polar equation for our circle with the center at -2, 1. Finally, let's talk about symmetry of polar equations. Before we begin testing symmetry, we need to recall that cosine of positive theta and cosine of negative theta are the same. Likewise, if we look at the positive angle and a negative angle, the sign of each one is different. The positive angle will have a positive sign, and the negative angle has a negative sign. And the cosine and sine of the sum of angles are given as cosine of a plus b is equal to cosine A cosine B minus sine A sine B, and then you can see the other formula for sine of A plus B. To show symmetry, we need to see which of the following are true. In the first statement, if r theta is equal to r negative theta, then the graph is symmetric about the polar axis, the x-axis. In the second statement, if r theta is equal to r pi minus theta, then the graph is symmetric about the pi over 2 line, or the y-axis. And finally, the third statement says, if r theta is equal to r pi plus theta, then the graph is symmetric about the pole, or symmetric about the origin. Let's determine symmetry of the following graphs. For example 6a, let's begin with r is equal to 6 cosine theta. We actually know what the graph looks like from both our exploration of polar graphs and from example 2a of this lecture. From the graph, we can see that the circle is symmetric about the x-axis, the polar axis. Let's see how we can discover this and other possible symmetries without knowing what the graph looks like. Algebraically, we will use the symmetry tests mentioned above. First, let's see what happens if we plug in negative theta in our equation. R is equal to 6 cosine negative theta. From cosine of negative theta is equal to cosine of positive theta, our equation remains the same as R is equal to 6 cosine theta. Because it remained the same, the graph is symmetric about the polar axis, the x-axis, as noted by the graph itself. Second, let's see what happens if we plug in pi minus theta into our equation. We're going to get R is equal to 6 cosine pi minus theta. Using the sum formula for cosine, we're going to get the following: 6 parentheses cosine pi cosine of negative theta, negative, minus sine of pi sine of negative theta. What we do know is sine of pi is equal to 0, so all of that is gone. And we know cosine of pi is negative 1. So this is going to reduce our equation to become 6 times negative cosine of negative theta, and that reduces to negative 6 cosine theta, because we know cosine of negative theta is the same thing as cosine of theta, and then we just multiply the negative on the outside. Since we didn't get the same thing, we realize that this is not symmetrical about the y-axis or the pi over 2 line. Lastly, let's see what happens if we plug in pi plus theta into our equation. We're going to get R is equal to 6 cosine pi plus theta. Again, we're going to use our sum formula for cosine. So we get 6 times cosine pi cosine theta minus sine pi sine theta. And again, we know sine of pi is equal to 0, and we know cosine of pi is negative 1, which means our equation is the same thing as R is equal to a negative 6 cosine theta, which is not the same as our original equation, so it is not symmetrical about the pole. Let's try another equation. First, we're going to plug in negative theta into our equation. So we're going to get R is equal to 2 sine of 3 times negative theta, which is the same thing as sine of negative 3 theta. Remember, for a negative angle, we're actually going to get a negative 2 sine of 3 theta, and we're going to see that that is not the same thing as our original equation, so therefore this is not symmetrical about the polar axis or the x-axis. Second, let's plug in pi minus theta into our equation. We get R is equal to 2 sine of 3 parentheses pi minus theta. 2 is equal to 3 pi minus 3 theta. So now I'm going to use the sum formula for sine. So I'm going to get 2 times sine of 3 pi cosine of 3 theta. Sorry, negative 3 theta, plus sine of negative 3 theta cosine of 3 pi. So let's see if we can simplify some stuff here. We know that sine of 3 pi is equal to 0. We know cosine of 3 pi is equal to negative 1. So our equation now becomes 2 times a negative sine of negative 3 theta. But we also know that if the angle is negative, then the sine is negative. So I'm going to change that to a positive. So it'll be 2 sine of positive 3 theta, which is actually the same as our original equation. So since it is true statement, we find that this graph is symmetrical about the pi over 2 line, or the y-axis. And we can see that in our graph as well. Finally, let's plug in pi plus theta into our equation. We're going to get r is equal to 2 times sine of 3 times pi plus theta. I'm going to use the distributive property, so I get I'm going to get 2 sine of 3 pi plus 3 theta. We're going to use the sum formula for sine, so I get 2 times sine of 3 pi cosine of 3 theta plus sine of 3 theta cosine of 3 pi. And we can see things can simplify. We know that sine of 3 theta is equal to 0, so all of that is 0. And cosine of 3 pi is negative 1. So that's going to give me 2 times a negative sine of 3 theta. And we can see that that's going to give me negative 2 sine of 3 theta, which is not the same thing as our original equation. So we know that it is not symmetrical about the pole or symmetrical about the origin. We could have also come to the same result if we knew what the graph of r is equal to 2 sine 3 theta looked like. We recall that this is a rose with 3 petals, each measuring 2 units, and said it is sine, we know that 1 petal is on the y-axis, as we can see from the graph. This concludes this video on converting polar equations into rectangular equations and symmetry of polar graphs and equations.